welcome to discussion 9 for CS61B. Today we're going to be talking about traversals, tries, and heaps. So before we get to the content, let's get some announcements out of the way. The first thing is that midterm 2 is next Wednesday, so soon. So please start studying now so you don't get caught by surprise this weekend. There was a topical review session on Monday. There will probably be more coming up soon, so keep an eye out for those. Lab this week is a project to work day. So you don't have to come. We'll have a little more people at office hours. So if you're struggling with your project, you should hopefully be able to get help quicker. But yeah. And lastly, ahead of the midterm, we have released a form for study groups. So please sign up so that you can meet some other people in the class. Let's get into some content review. So we've been talking a lot about things like binary search trees and B trees and all these very specific types of trees. But let's talk about trees as a whole, as a more general type of structure real quick. So trees basically only follow two rules. The first is that if there are n nodes, then there are n-1 edges. And the second is that there is always exactly one path from every node to every other node. And this basically ends up meaning that trees are fully connected, so there's no random node out there that's not connected to anything in our tree. And they contain no cycle, so you'll never have a situation where it's like something pointing like that. That doesn't happen in a tree. Some terminology that may be useful as you learn more about trees is a parent node is for instance, in this node relationship, this is the parent node, and this is the child node, which makes sense. A parent points towards its child. You can kind of think of it like a family tree. The root of a tree is a node with no parents. So this top node right here is the root of this tree, and a leaf of a tree is a node with no children. So both of these nodes down here, also this node up here, are all leaves because they're basically like the end of a tree. There's nothing beyond this point. So how do you move around a tree? How do you figure out what items are in a tree? So there's two main types of search we use when it comes to a tree. And the first is called breadth-first search. Breadth-first search basically means that we visit the nodes in a tree level by level. So we basically go level 1, level 2, level 3, from left to right. And when you think about how you do breadth-first search, you usually do it using a queue. And we'll get back to this with more detail when we talk about graphs, either next week or the week after, and we do breadth-first search there. But yeah, this is how breadth-first search is done. And the second one is depth-first search, where you can think of breadth as being going going level by level. Depth-first search is the opposite. You shoot all the way to the bottom first, and then you come back up and figure out what you've missed. So DFS, depth-first search, can be done 3 different ways. The first is called pre-order, and pre-order means you visit yourself before you visit your children. So in this tree right here, you can see we visit A, and then we visit its children B and C, and then we visit C's children D and E. Pretty straightforward. In-order traversal, on the other hand, means you visit the left child, and then the parent, and then the right child. And this is useful for things like binary search trees, because this allows us to list out all the items in a binary search tree in order, which is why it's called an in-order traversal. So in this case, we would basically go to B, but we wouldn't visit it. So if we were writing a function, perhaps the visiting would be printing, but we would recursively go to B, but we won't have printed it yet. First, we'll make a call to A. So we'll call the function on A, and then we'll print A, and then we'll return. And once we've returned, we can print B. And once we've printed B, we can call the function on its other child, D. And again, we won't do anything with D yet until we've called the function on its left child. And then we do the action, and then we come up here, and now we can finally print or whatever we want to do to D, and then we can call it on this child. And that gives us the ordering we see right here. The last ordering is post-order traversals, which is the opposite of pre-order. You visit both of your children before you visit yourself. So in this case, like I said before, we'll enter this node, but we won't visit it yet. Let's say we won't print it yet. The first thing we'll do is we'll call it on its left child. And obviously A has no children, so there's something to call it on. So then we can visit A. Now that we've done that, we can move back up to E, but we still have not seen all of its children. So we're going to call whatever function on its other child. And just like we did with E, we have to call it on first its left child, which we then visit and return, and then its right child, which we then visit and return. And now that D has no more unvisited children, we can finally visit E. We can finally print out D or whatever we want to do, and return back to up here and do E. Depth first search is usually done using a stack in general. And again, like with breadth first search, we'll get into more detail about this next week or the week after when we talk about graphs and traversing those. So let's talk about some special trees. So the first special tree that we're going to talk about is tries. And tries are special trees that are mostly used for language tasks. Each node in a trie is marked as being a word end or not. So in this case, for instance, T is marked because cat is a word. H is marked because catch is a word. G is marked because dog is a word. And this other G is marked because dig is a word. And so this is just allows you to quickly check whether or not a word exists within your structure. Where is this used? Not too often. It is a very specific data structure, I'll admit. It is used for things like what you'll do in Project 2, I believe, which has to do with word completion and stuff like that. But it's just an interesting thing to know, and it comes up in interview questions often because most schools don't teach it. So now you know what a trie is. Moving on to heaps, which are a little more important. Heaps are special trees that follow two basic rules. Heaps are complete. So basically what this means is that you can put the items in a heap in an array. Like this is the first item, second, third, fourth, fifth, sixth, kind of going row by row. And there won't be a single gap in the array. Everything will be filled. And that's what complete means. So complete ends up meaning that all gaps in the heap are to the right bottom corner of the tree. In a min heap, every node has to be smaller than both of its children, and in a max heap, every node has to be bigger than both of its children. So keep in mind that heaps don't work like search trees. You can't quickly find anything in them because all you know is that every node that is under 0 is less than 0, or greater than 0. So you don't really know where it is. It's not a search tree. It's used only for quickly being able to pop out the smallest item or the biggest item. Insertion into heaps is a little interesting, so we'll go over it real quick. So when you insert into a heap, you always add it to the empty slot, the next empty slot. So if you're viewing this in array form, it'd be like 0, 1, 2, 3, 4, 5, and then you'd insert it into the 6th spot in the array. And now that it's there, we know that this is a general structure the heap is going to have, but this specific node is just in the wrong place. So we're going to swap it up with its parent up until we hit a point where it is either at the root of the tree or it's no longer smaller than its own parent. And of course, it's the same process you would use for a max heap, except for a max heap, you would be checking whether the node is bigger than its parent rather than smaller than its parent. Deletion is a little bit similar, but it requires just one trick at the beginning. So when you delete a node, what you do is you take the last node in your heap, so in this case it's this 4, and you replace whatever you deleted with that node. And now that it's up there again, This is a general structure that's going to persist with the heap, but your nodes are just in the wrong place. So once you've done that, you check to see whether it's smaller than both of its children, and if it's not, you swap with the smaller child. So in this case, you swap with 1, and then you swap with 2, and now the heap properties are back in order. So that was some content, but now we can move on to the worksheet. This is a lighter worksheet, so hopefully it won't take too long and you guys can focus on studying for the midterm. So the first question is, we are given this tree structure and I want you guys to write out the pre-order, in-order, post-order, and like level order or breadth first search versions of this tree. So I'll give you guys a minute to think about it, and then when you're done, we can reconvene and talk about it. Okay, welcome back. So let's start off with pre-order. So the first thing we're going to do, let's write down pre-order. So the first thing we're going to do is count. So first we're going to go here, and we're going to visit it immediately. So we're going to add that to our list. And now we're going to visit its children in order. So we go to 3, and we just visit that straight away. So we have 3, and then we go to 1, visit it straight away, 7, straight away, and then we do the same for this tree. So then we'll get 12, go down here, 11, here, 14, 13, and 15. The next one we're going to do is in order traversal. So again, for in order, we will start at 10, but we won't quite visit it yet. Let me just write down in order. So we're going to go to 3 first, but again, we're not going to visit it because 3 has a left child. So we're going to go down here. We're going to visit this, pop it over there, go back up, visit 3 now that we visited its left child. And now we're going to go to 7, mark that. And now that we're done here entirely, we can pop up to here and visit 10. And then go down here and go to 12 without visiting it quite yet. And go to 11, back up to 12, down to 14, down to 13, visit 13, back up to 14, and down to 15. And now we're done doing a traversal of this tree. The last one in the depth first search category is going to be post order. So for post order, remember we visit both of its children before we visit each node. So we're going to start at 10 without visiting it. We're going to move down to 3. And again, we're going to see both of its children. So 1 has no more children, so we can just immediately visit that. Pop back up, go down to the other child, visit 7, pop back up, and now we can finally visit 3, and now we can pop back up to 10, but 10 has another child still, so we're going to go down to 12, and now we're going to go down to 11. And now that we're done with 11, we can pop back up to 12 without visiting it quite yet, and go down to 14, and then down to 13. And now that we're done visiting 13, pop up to 14 again, down to 15, back up to 14. Finally, all of 14's children have been visited. Back up to 12, finally all of 12's children have been visited. And finally back to 10, because all of 10's children have been visited. And lastly, we're going to do just a breadth first search traversal. So again, that is row by row going from left to right. So in this case, BFS, we'll go as 10, we'll go this way, and then through these two nodes, so we'll get 3 and 12. And then we'll go across these 4 nodes, so we'll get 1, 7, 11, 14, and then across these nodes, so we get 13 and 15. So if you look at this, you can see that our in-order traversal in fact returns the nodes in sorted order because we're working with the binary search tree. And you can kind of see how we got pre-order, post-order in BFS. Next, we're going to move on to a question about tries. So the first question that we can just kind of do together is, what strings are stored in the try below? Well, remember, when we're looking for what strings are stored, we look for these marked nodes because they mean that they are at the end of a word. So that means we know that the first word goes from here to there, which is index. The second word kind of goes like that, which is inch. And the last word goes like that, which is info. So the question here is, how would you insert indent, inches, and try? I'll give you guys a second to think about it. Okay, welcome back. So, hopefully you guys have something written down. So for indent, the first thing, we will just follow the path as far as we can. So we start off with I, we visit I, and then N, and then D, and then E, and then we see that there's no N for us to go to. So we have to create that node. So we can create an N node, and then we can create our T node. And this one we can mark as being the end of a word. Up here, now we can add inches, and we can do the same thing. So we have I, N, C, H, and then there's nowhere left to go, so we have to add nodes for the E and the S. And the S gets marked as the end of a word. And the last thing we're going to add is try, and there is no T at all currently, so we're going to have to add the entire word. This acts like a sentinel almost, which holds the initial connections to the first letter. So we're going to connect straight out of there, T, R, I, E. And of course, we're going to mark the E as the end of a word. Now the real question is, how could you modify a try so that you could quickly determine the number of words that have a specific prefix? I'll give you guys a minute to think about it. Okay, so welcome back. So I hope you guys try to come up with something, but the solution that I have, which is probably not the only solution, is to include a counter at each node. And what that counter will be is the number of words that pass through that node. And so what you would do whenever you added a word is you would just, like for instance, if we're adding indent, we would just add one to every counter along the line up until we hit our end. And that way, we will know that, for instance, there's 2 words that start with IN. Pretty simple. And then when you delete, all you have to do is go right back up the same line and make sure that you're subtracting 1 from each of the nodes. Great. So this will take very little time, theta 1 time to figure it out. It was a great solution, but there are probably others, and I urge you to see if you can think of another one. Now our last question, I told you this worksheet was pretty short, is called Heaps of Fun. So I'm going to ask you to create a character heap here, where let's say that characters that appear earlier in the alphabet are like smaller than characters that appear later. So A is less than B. And I want you to insert, in this order, the characters into your min heap and then remove min twice and tell me what you get. I'll give you guys a minute to think about it. Okay, so the first thing we're going to do is insert F, which is all alone, so there's something to do here. And now we can insert H. And of course, we know that H comes after F, so there's nothing that we have to do here. And the next thing we're going to add is D. And like always, we add it to the end of our heap. And of course here, D is less than F, so we're going to swap these two. And now everything's in its rightful place, so we can stop swapping. Next, we're going to add B. And again, we're going to swap. So B and H are going to swap. And this time, B is also, B is also less than D. So we're going to swap it right there and get a tree that looks like this. Now that we've done that, we're going to add C. And of course, we're going to swap C and D immediately and end up with this tree at this point. So now we're going to remove min, which obviously removes B. So we're going to get rid of this node up here and replace it with D, because we're going to take the last node and pop it up to the top, and now we're going to sync it. So D is less than C, so we're going to swap those two and get C and then D. D is greater than H, so this is it. And now we're going to remove min one more time. It's going to give us C, and this time we're going to pop H up there, and we're going to sync H. So D is the smaller child, so we're going to put H down here and D up there. And that should be your final structure of your heap. Now, your last question for today is, I will challenge you to quickly implement an integer max heap data structure. However, your underlying data structure should be a min heap, and you can't change anything but the min heap. So imagine I let you import min heap, and that has to be your underlying data structure. You're not allowed to use any other data structures. How could you make an outside user think they were working with a max heap? I'll give you guys a minute to think about it. Okay, welcome back. So there are actually a couple good answers to this problem. The most common one is to negate it. So have your underlying min heap, and every time someone adds something to your max heap, you just negate it, right? Because a big number becomes a very, very small number when you take its negative, and vice versa. And so this will basically create an inverse min heap, which is a max heap. And then when anyone removes max, you just pop the minimum item and then negate it again, which will give you the original item, and return that. Another option, which was pointed out to me during my section, which I thought was really interesting, was taking the inverse. So you would go 1 over whatever number. Of course, in that sense, you have to hope that you have access to a double min heap or float min heap. But since we don't specify in the problem, this could work as well. So just like negation, if you take the inverse of a very large number, it becomes a very small number, and vice versa with a small number. And so any operation that causes big numbers to become small and small numbers to become big will work in this scenario. Okay. So that brings us to the end of our discussion. I hope you guys have a great week. I hope you guys do well on the midterm, and I'll see you guys next week.